Good day, and welcome to our webinar on how the right seal face technology overcomes process challenges and extends equipment life. Today's program is brought to you by CFE Media and Technology and sponsored by John Crane. Joining us today from John Crane is Brian Calfrin, a Senior Regional Engineering Manager, and Jack Pagane, a Senior Staff Mechanical Engineer. I'm Kevin Parker, an editor with CFE Media and Technology. During industrial processing operations, every mechanical seal application experiences its own unique set of challenges, including inadequate seal face lubrication, high heat generation, and dry running conditions. These issues can cause leakage, unplanned equipment downtime, and even catastrophic equipment failure, negatively impacting operations and profitability. Mean time between repair intervals for mechanical shaft seals can occur frequently in these harsh conditions, which means maintenance costs go up and equipment runtime goes down. Stay tuned to this webinar to gain insights based on expert knowledge and real-world case studies that will be of use in your plant, mine, or mill. To get the best results from the webcast platform, please make note of the following as you participate in today's event. If you are having technical problems, click on the question mark at the top right-hand corner of your screen to bring up a list of system checks to make before escalating to an online technician. If you are experiencing issues with the slides or audio, please refresh your browser or click the Refresh Media button directly under the presenter's headshot. You can control the volume settings of this webcast by adjusting the volume of your computer or by adjusting the volume on the webcast platform itself. If you do need a technician, type a message into the Ask a Question box, and someone will get to you as quickly as possible. Answers to technical questions will appear in the Answered Question box on the left-hand side of your screen. The Ask a Question box is also used to ask the speakers questions. You may ask questions at any time during the presentation. We'll get to as many as time allows. To download the presentation slides and certificate of completion, use the Event Resources box on the left-hand side of your screen. You can download the presentation and certificate of completion until the conclusion of the webcast. The link will break when the webcast signs off. This webcast is being recorded, including the Q&A session. We'll send you an email message within a week with a direct link to the webcast archive. I'd now like to introduce today's speakers. Brian Calfrin is a Senior Regional Engineering Manager with John Crane in Pasadena, Texas, with more than 18 years' experience with mechanical seals and related systems. He is responsible for engineering expertise within the Gulf Coast region of the United States. His duties include design engineering oversight, analysis, and recommendation formulation to address challenging problem applications, along with design evaluation of existing and proposed mechanical seals utilizing finite element analysis. He is also responsible for training of both customers and John Crane personnel in both mechanical seal application and troubleshooting. Brian is a member of the Texas A&M International Pump User Symposium Advisory Committee, the API 682 Task Force, which is currently working on the 5th edition, and a degreed mechanical engineer with a BSME from Drexel University in Philadelphia, Pennsylvania. Jack Pagane is a Senior Staff Mechanical Engineer with John Crane in Morton Grove, Illinois, with more than 30 years' experience with mechanical seals and related equipment. He joined John Crane in 1989 as an applications engineer and progressed to various engineering roles with the company internationally, supporting refineries and petrochemical facilities in Saudi Arabia, Kuwait, Dubai, and Bahrain in the design, selection, and troubleshooting of both wet and dry gas seals and support systems. Jack is an active member of the API 682 Task Force, currently working on the 5th edition of the standard, and he is chairman of the Mechanical Seal Committee at the Hydraulic Institute. Jack holds a BSME from the University of Illinois in Thermomechanical Engineering and Energy Conservation. Jack, welcome to today's webinar, and please go ahead.
Thank you, Kevin. Is it possible to have one seal design that can handle all my pump sealing requirements? This is a question we normally are asked by end users and many plant personnel every time we actually visit a plant. However, in the process industry, there are many challenges that need to be addressed when selecting and designing a mechanical seal for a given pump application to achieve a reliable operation. By far, the most challenging aspects of seal selection are due to the nature of fluids themselves. The processes of these fluids, such as pump temperature well below minus 20 degrees, it can even go down to minus 260 degrees Fahrenheit in the cryogenic services, pump temperature above 500 or even reaching above the 500 to 800 degrees Fahrenheit, specific gravity below 0.7, and sometimes in the light hydrocarbon even below 0.3. High or low viscosity applications, low vapor margin. Normally with API 682, the recommended margin when you're sealing the light hydrocarbon should be about 30% above seal chamber vapor pressure. Abrasive particles, high pressure, 1200 to 2000 psi, and the pipeline could be higher than that. Multi-service pipeline, wide viscosity ranges, and high viscosity oils and wide pressure ranges. And in the pipeline, you have identical pumps often in series, which means that multiple pumps will have the same mechanical seal, however, different application or the pressure-wise, and remote location requiring auto startup. Now, depending on the process industry, i.e. the oil and gas, chemical process industry, wastewater, mining, etc., each will have some challenging application that require special design and or sealing solution. Some of these applications, I'm not going to list all of them, but you have quite a few of them. You have quenched oil, tower bottoms, where you have coking problems, demethanizer bottoms or reflux or deethanizer reflux pumps, or very cold, low vapor margin and low lubricity. Ethane or ethylene were very high pressure and low vapor margin as well. Heavy crude oil, atmosphere, vacuum tower bottoms, or coker charge pumps, going down to, let's say, HF acid in the alkylation services, where it's very corrosive and lethal when it comes in contact with humans. Sulfur services, corrosive, and it has a very odd property when it comes to viscosity, whereas viscosity can swing quite rapidly with minimum temperature change. Produced waters normally is abrasive and high pressure and often corrosive. And well injection is also high pressure and abrasive, and pulp and paper process where it's caustic and abrasive and low lubricity. First of all, let's look at the mechanical seal and understand the mechanical seal before we can, look at the reliability of these mechanical seals. The mechanical seal consists of a number of components. When the seal is actually static, there's normally no leakage. You can see the fluid in the pink side. The fluid is normally on the outside diameter in the mechanical seal, or if we call it the pressure side of the mechanical seal. And the atmospheric side is on the other side. Now, the heart of the mechanical seal are the two components that we normally call faces. We take these faces and look at them as far as design is concerned. Now, to understand the fundamental principle of how a mechanical seal actually operates and what factors affect the reliability of the mechanical seal, let's take a look at the simple axial force equilibrium of that mechanical seal. It's normally assumed that the sum of the axial external loads, i.e. the process pressure, the spring force, and the secondary seal frictional force is supported by a fluid film between Sorry about that. Somehow it actually jumped in. Supported by a fluid film between the seal faces, sorry. However, for most mechanical seals, the fluid film, sorry about that. Anyway, we'll continue on. So for most mechanical seals, the fluid film or hydrostatic pressure and hydrodynamic pressure effect is not strong enough to actually support the full closing force or the axis, and the axis is supported by the asperity contact between the sealing faces or sealing rings. The seal must run with lubricating fluid film between the sealing faces. Controlling of this fluid film is crucial when it comes to a successful operation of a mechanical seal. This gap, H, presented here, is very small, few microns in reality. When closing force is too high, the leakage is reduced. However, frictional heat generation increase, leading to a high face wear. Now, if the opening force or the supporting force is high, the gap increases, leading to a high leakage rate. We look at that leakage near Q. It's normally seal leakage is proportional to the sealing gap, HQ. So in reality, it's very critical to control this gap, as if we double the size of this gap, because of the Q, it's actually 8 times higher face leakage. If it's triple, only a few microns, it can be 27 times the leakage. So let's take one of the applications in there that's quite critical when it comes to mechanical seal. So in a light hydrocarbon service, it's probably one of the more challenging applications for a mechanical seal. In light hydrocarbon, maintaining, as we mentioned earlier, the fluid film between the seal faces, it's a key for reliable seal performance. When you use a plain seal face, there's usually product can vaporize across the sealing interface. How is that possible? If you look at the pressure profile, the top of the pressure profile is where you're sealing that liquid or the light hydrocarbon. As the liquid travels through the interface, it reaches a point where product reaches its vapor pressure. That will lead the product to actually vaporize. And by doing so, you minimize or reduce the liquid film between the two seal faces, thus generating high frictional force, frictional wear and damage to mechanical seal. How do we overcome that? Normally, what we recommend is a Hydropad seal design, and this technology was on a long time ago. Hydropads are actually recesses that are machined into the seal face, similar to a half moon shape. They promote lubrication by maintaining fluid film. If you look at the pressure profile again, by introducing that cutout into the face, you actually inject or introduce more fluid all the way down into the sealing interface, thus providing more liquid or maintaining a fluid film all the way across and minimizing the vaporization of that liquid. Secondly, we look at a newer technology from the Hydropads, and this is what we normally call a laser face technology. This is a sealing interface technology with inlet and a return flow groove pattern. So the challenge is actually improving the interface lubrication and hydrodynamic fluid film support at low or similar low level of leakage for single or tandem mechanical face seals. The solution: interface microgrooves with independent hydrodynamic lubrication, enhancing inlet, and a flow groove that leakage reduce return flow groove. Now, if we look at that picture over here, I would like to actually, explain more on the functionality of the laser face. The laser face pattern combines a pair of symmetrical, precision-machined microgrooves, typically a few micrometers deep. They're not as deep as Hydropads, each of which performs a different task. The square inlet groove is normally connected to a pressurized fluid area, and through it, the process can actually penetrate deep into the sealing interface. This fluid then is actually tangentially dragged by the sliding counterface, and as soon as it reaches the edge of that square groove, it generates a hydrodynamic pressure. That pressure lifts the seal face, creating a stabilized fluid film, thus guaranteeing low friction and low wear. Then, the semicircular groove downstream of that square groove is also known as a return groove, re-injects the majority or the excess fluid back into the process or the pressurized process, thus minimizing the leakage. Now, let's compare the three different types of or shapes of mechanical seals or the technology: plain face, hydropadded face, and a laser face. And we take the two critical situations where you have high heat generation and leakage. If we take that as a percentage of maximum value, in a plain face, due to the fact that you have a wide face, the frictional forces generate high heat. So by generating the high heat, again, the seal is wide enough. It does give us low leakage. However, high heat generation can actually damage the mechanical seal, and eventually you will have, a catastrophic failure. When we use hydropads, by introducing more liquid into the interface between the two seal faces, you minimize the heat generation. However, you increase the leakage. Laser face, however, takes into consideration that when you have the inlet groove and the return groove, you minimize the leakage, and at the same time, by introducing the liquid or more liquid into the interface, you have reduced the heat generation, thus a more reliable seal performance. Now, as an example, taking two seals, an enhanced and a conventional or a laser face, 100 millimeter seal, going with a speed of 3,000 RPM in mineral oil, using exactly the same pressure, spring face, and balance ratio, a calculated torque will show that an enhanced or a laser face torque is less than half that of a conventional seal. And this is actually shown in the graph above. However, leakage is about 1.5 to 2 times higher than a conventional seal. In a smaller seal shaft size, in water, we did another, look at another test. Pressure again is the same, spring pressure is the same, and the equivalent balance is the same. Again, the torque is half of that of the conventional seal, and the leakage was minute on both of them due to the fact that the seal is quite small, and the leakage is relatively small. Now, that is theory. Let's look how that works in practice. We have taken these seals and actually put them through our test facility using a 2-inch seal, conventional standard mechanical seal, with a 2-inch laser face seal. Again, the seals are identical except for the laser face grooving on the mating ring. Speed was 3,600 RPM. We used the media was propane at 56 degrees C and a 21 bar G pressure. API flesh plan was actually used to cool the seal at 10 liter per minute, which is a bypass from discharge. And we ran these seals for 200 hours. In comparison, this test, comparing it to a qualification test for API 682, normally API 682 is using propane. The saturated vapor point of the propane is shown here in the red line. API 682 recommends about 30% margin higher than vapor pressure. and that's represented by the yellow line. And the qualification test for API 682 was 17 bar at 30 degrees C. However, in our test, we have gone into a higher pressure and closer to or less than 30% margin for the seal vapor pressure. After 200 hours, we have tested the seal and looked at the post-seal examination. In a conventional seal, we noticed that there was 0.3 millimeter heavy carbon wear in 200 hours. Light blister at carbon face is shown in slide 1 and 2, and a small chip, and this is actually magnified, on the ID of the carbon face. Mating ring shows polished running track from dry running operation due to the vaporization of that liquid again, and approximate seal life based on the face wear was about 3 months. In the laser face post-test examination, we have noticed that there was a very light carbon wear, about 0.003 millimeters, almost negligible, mainly polishing. Very light polishing of tungsten carbide mating ring. No material reduction can be measured on both, so approximate seal life based on face wear was 274 months. So potential application for laser face is a service where poor interface lubrication lead to a premature seal failure on a single and a tandem mechanical seal. The seal is normally used in hot water and light hydrocarbon services. The high-duty double seals also as a mean to increase reliability, reduce hang-up, and extending the pressure velocity or PV limits, as we call it. The limitation of the seal is only for liquid service, and it has to be solid or abrasive-free fluid. It has to be clean fluid. And I might also add that the laser face technology can be applied to most of conventional seals or most of the seals already out in the field. The next one is a spiral groove technology, that enhanced technology for high vapor pressure pump application. This spiral groove technology was actually driven from gas seal technology, where you have a spiral groove that generates a liftoff and the seals are normally running dry, are running non-contacting, running on gas cushion. This seal, the spiral groove, is designed, or the design is actually identical to the laser face, except the primary seal mating ring. The spiral groove in this seal, again, as I mentioned, is similar to a compressor gas seal. The shape of the spiral groove, when it's operating, it drags the fluid or the gas or vapor into the spiral groove. Once the process fluid reaches the bottom of the spiral groove, it generates hydrodynamic pressure, and that pressure overcomes the closing forces and pushes the seals apart, the faces apart, creating a non-contacting seal operation. If you look at the blue and the green at the bottom of the grooves or the ring here, it shows the peak pressure is at the bottom of the spiral groove, and that's where the lift is being generated. This seal is normally available or only available as a dual seal and an unpressurized dual seal, and a preferred arrangement includes a dry running containment seal. So the spiral groove seal are specifically designed to cope with condition of the majority of high vapor pressure application, ethane, ethylene application, where you have high pressure and low temperature margin of pumped product, that the seal can actually is designed to run on liquid fully flooded and occasionally full vapor. However, most of the time we find that with full vapor, the leakage is much less than when the product is actually fully liquid or fully flooded seal. The seal is designed to cover typical duty condition for flashing light hydrocarbon covered by API 682. Typical application, high vapor pressure hydrocarbon, ideally above 1 bar at room temperature. Low specific gravity, again, that can be even below 0.3 specific gravity, and it's normally recommended with specific gravity below 0.6. Typically, temperature margin less than 6 Kelvin of saturated vapor point. Pressure, which is API 682 to 41 bar. However, we do have mechanical seals out there running at a much higher pressure than that with slightly different configuration. Temperature minus 40 C to 260 C, and or minus 40 Fahrenheit to 500 degree Fahrenheit. Arrangement, vertical or horizontal pump. Application where no or only limited seal flush can be realized. Limited radial space, very low pressure differential between suction and discharge. Application, again, where seal reliability and life are predominantly selection criteria over inboard seal leakage. Now, the seal is designed to operate non-contacting. Therefore, the primary seal leakage is approximately 50 times that of a conventional mechanical seal. However, the actual seal leakage to flare or vapor recovery system will be dependent on the actual makeup and the makeup temperature on margin of sealed vapor pressure or sealed saturated vapor point of the pump fluid. The outboard seal leakage is normally a non-contacting. This is a preferred, and that seal is normally normally runs on either nitrogen or what have you, with a process pressure about not exceeding about 10 psi. The leakage to the atmosphere with that containment seal is less than 200 parts per million.
Well, we're going to move on to talk about dynamic lift upstream pumping technology. And it's a rather unique technology using an application of spiral grooves in a slightly different fashion. Jack talked about utilization of spiral grooves for high vapor pressure. So now we're going to go into a slightly different application as well and talk about that a little bit. So with the dynamic lift upstream pumping technology, we are utilizing spiral groove technology once again. When you have spiral grooves in a mechanical seal, you're typically looking at three kind of applications for spiral grooves. One is the traditional case of a dry gas seal in a compressor, where you would be sealing a gas with a gas in your dry gas seal. You can also use spiral grooves in a centrifugal pump with a pressurized gas seal, and in that case you're using a gas to seal a liquid. The third example would be utilizing your spiral groove technology to seal a liquid with a liquid. So we're using a liquid-on-liquid application of hydrodynamic spiral grooves, and what we call that is a dynamic lift upstream pumping seal, or a USP seal. And it's called upstream pumping because there's deliberate upstream migration or dynamic lift of a lower pressure clean fluid to a higher pressure region within the seal chamber, and we'll talk about how that works in the next slide. There are some advantages to approaching an application with this type of face treatment. Really, we're getting the advantage of a dual pressurized seal and bringing that to an unpressurized support system. The actual pressurization of that low pressure fluid is achieved by the seal faces themselves, utilizing the geometry of the spiral grooves. When we look at the application, there's very low heat that's generated by the seal itself. And because of the USP technology, the conventional PV limits that would be applied to an inboard seal, they're usually ignored because the USP grooves ensure full face lubrication during dynamic operation. And the overall duty on that mechanical seal is much lower because you don't require such high pressurized barrier fluid applications to overcome high pressures in the seal chamber. So there's lower outer seal consumption overall than compared to, say, a plan 53A, B, or C. So how the technology works is, if we look at a side-by-side example of a conventional seal on the left and a dynamic lift USP seal on the right. Conventional mechanical seals got lap faces. They're lapped within 2 helium light bands one helium light band is 11.6 millionths of an inch, so very precise measurement. And that mechanical seal operates by utilizing the process fluid to support lubrication of the seal faces at the interface. So typically you have a gap of about 3 to 4 microns between conventional seal faces. The upstream pumping is so called because of the principles reversed, and we're now taking a chosen fluid and pumping it from the atmospheric side of the seal faces upstream to the higher pressure process fluid. Now, how that is accomplished is by utilizing the geometry of the groove and some basic fluid mechanics in terms of what happens when we try to compress a liquid. We're going to generate a fairly substantial amount of pressure. And you can see as liquid would enter these spiral grooves, the pressure will increase as that liquid will migrate to the tip of the groove through shaft rotation. So what happens is as the pressure is increased, the flexibly mounted seal face is going to lift and separate a little bit, and that's what sets our gap between the seal faces. So the maximum pressure always occurs at the outside diameter of the grooves, and it's always higher than the process pressure when the seal is operated within its parameters and it's in a dynamic state. If we look at an example of this technology in a real-life application, what we have is a desalter water application here, which is about 200 degrees F for the process temperature, 195 psi in the seal chamber, 3,600 RPM, and only a 10-month MTBR. So not an ideal mean time between repair for this particular application. The seal itself was utilizing an API plan 41 and 52. API plan 41 is not an ideal piping plan, and it is recognized as not being ideal in API 682 itself. It utilizes a cyclone separator in conjunction with a heat exchanger to try to provide a better environment for the seal in terms of lowering temperature and removing solids. While in the case of desalter water, where you have not a good lubricant to begin with in terms of high temperature water, and you also have solids in solution, cyclone separators are not going to do well in that environment to remove those solids. And with essentially a Plan 21 portion of that Plan 41, constant injection of high heat to the heat exchanger creates a lot of high loads on the heat exchanger and not a very efficient piping plan. Your typical mechanical seal observations from this pump, when you look at the pictures on the screen, what you're seeing is essentially indications of high heat loads present due to localized temperatures. Because your liquid goes away due to the high localized temperatures, you're leaving behind a lot of entrained solids and debris. So this supports the theory of venting concerns and not an optimal piping plan for this particular application. So in this instance, the owner of this equipment was looking for a solution that they could kind of implement rather quickly, and they had existing mechanical seals in their inventory that would actually fit into this pump, and that's what's pictured here. But the only adjustment that was made to this mechanical seal was the application of the dynamic lift upstream pumping grooves to that inner seal face, that inner mating ring stationary face. And by utilizing the existing seal and retrofitting it with the USP technology, it came up with a rather unique solution for this application. The support system was relatively simplified. It just consisted of a dedicated line of water or clean condensate piped directly to the reservoir that you see in the picture, and then a regulated pressure of 5 psi on that dedicated water line. So over time, as there was some consumption of the water by the upstream pumping grooves, and the typical consumption rates are very low, between half to a gallon per day usually, or a few gallons per day depending. But as the seal consumed the water, the regulator will open up to adjust and equalize that pressure. So what you're looking at here is a very reliable support system that's using 5 psi of a low pressure buffer fluid to seal 200 psi in the seal chamber with no loss of containment and no leakage of that hot salty water to the atmosphere. So the implementation of this solution resulted in an MTBR of now 5 years and counting. So very reliable and very simple support system and sealing solution at the end of the day. John Crane's done quite a bit of testing with USPs on some very significant applications, such as slurry applications, and you can see this is kind of a stripped down post-mortem of the slurry seal rig, and you can see a lot of the abrasive wear and damage to the rig components themselves, just to the nature of the slurry, very abrasive particles. So what the thought here was, and the intended goal was to test the USP technology and see if the seal faces would suffer any adverse effects from being exposed to a very arduous duty, which is the slurry duty. And post-test inspection, you can see very clean and clear seal faces after this test running on a very abrasive slurry. So no adverse effects to the seal, and again, a good representation of the capability of this dynamic lift technology. There's several other case studies that are available to review and kind of compare some different applications, and these can be viewed and downloaded at the website you see before you. I won't go into every one of these right now, but just want to provide that information for future reference. So next seal face technology I'm going to touch on is something called a Y spiral groove. A very unique seal face technology. On the right hand side you see a high-speed turbo expander, and this would be kind of a typical application for this particular face technology. A lot of high-speed turbo machinery, compressors, expanders. Many of these applications these days utilize dry gas seals, and get rid of conventional kind of wetted systems and so on, for good reason. However, there's many machines still out there that utilize oil seals and conventional mechanical seals, and that in and of itself poses some challenges when you talk about conventional sealing technology. So when we look at oil sealing, there's some issues and some challenges we have to overcome. When Jack was talking about seal faces and requiring full fluid film lubrication, and we want to manage heat generation and leakage, well, in a application that's very high speed with oil, it becomes very unique and difficult because of some of the limitations around conventional end-face mechanical seals. So typically, from a material perspective, most seal designers and suppliers would like to utilize carbon for at least one of the seal faces, because carbon tends to wear in and have good lubricating properties, and also tends to provide the lowest leakage. When we're talking about an oil sealing application such as this, typically the viscosity is too high for carbon, even an antimony filled carbon, so we run into the possibility of blistering and causing damage to the carbon. And so then we have to look at alternative materials, which would be typical hard faces like silicon versus silicon, or tungsten carbide versus silicon carbide. Well, when we go to hard faces tend to develop a thicker fluid film just because of the finishes and the requirements of those two tribological pairs of materials. So with thicker fluid films, leakage becomes a concern. So if we try to minimize leakage by, say, now increasing hydrodynamic phase balance, we can possibly reduce leakage, but the trade-off is that we create more heat, because now we're pushing that oil We're creating increased heat from shearing of that oil, increased face temperatures. We may get some plating and unwanted face contact. So face contact, in this case, at 13,000 RPM would not be an ideal situation. In addition, John Crane's done a lot of in-house testing on hard faces at high speeds, and you really need to be cognizant of the centrifugal effects as you go higher and higher speeds. The centrifugal effects eject that oil further away from the seal faces. So you need to ensure that you have enough differential pressure at the seal faces to ensure that you create a fluid film for lubrication, but at all times we want to manage leakage expectations to within required parameters. So one way to approach that in a different fashion is to use something called a Y spiral groove. So what you see is a combination of both upstream and downstream grooves. And what we've created with this Y groove is a combination of downstream and upstream grooves in terms of we'll have feed grooves that will enhance liquid lubrication. We're channeling oil flow from the higher pressure side of the seal, and that oil flow that's channeled meets at that intersection of that upstream return groove. And as we meet that intersection and we channel some of that oil back to a termination point, we create a higher pressure due to that groove tip termination. And at that higher pressure, with that pressure spike, you're creating hydrodynamic load support purposely. And by doing that, you add a lot of stability to the overall seal face, and you're ensuring lubrication and stability of the interface gap. What you're also doing by utilizing that upstream groove is that fluid tends to take the path of least resistance and doesn't migrate to the lower pressure side of the seal. It will return its flow back to the higher pressure side, so your leakage is much less than comparative plain face seal designs in these applications. We have an example here of a FEA simulation of a 12,000 RPM oil seal application, and these are typical conditions: very high speeds, but relatively low differential pressures. There's only 50 psi in terms of differential pressure across that seal. So by application of the Y spiral groove, we're targeting very low contact pressure, so we have essentially zero contact pressure, no asperity contact, so that our entire fluid film is based on hydrodynamic load support. And then that generated pressure distribution at the termination point of that groove is going to migrate oil leakage away from the lower pressure regions of the seal. So by looking at this, the seal face equilibrium is established between our force balance between hydrodynamic and hydrostatic opening and closing forces. And then we got high pressure spikes that show that pressure generation at the peaks with this low DP application. So this is a actual example, application example of Y groove technology for a wet gas compressor using an ISO 46 lube oil, 50 psi of differential pressure, and between 7,000 and 13,000 RPM in terms of the speed range. Now the actual measured leakage of the seal you see here with the Y groove technology was less than 5 gallons per day, and that is a reduction from over 50 gallons per day with the previous seal, which was a plain face design. So when you calculate those numbers out, you're looking at a savings of roughly $250,000 a year just in reduced oil leakage. And just a worthy note here, the seal you see here is not overly complicated in terms of the design. What's very novel about design is the application of the Y groove technology to one of the seal faces. The last technology we're going to talk about is diamond face treatment, or John Crane diamond seal face treatment. So what is a diamond face treatment? So it's really unique technology in terms of this is not a coating or something that's sprayed on a seal face. This is surface engineering, if you will. It's a surface treatment where polycrystalline diamond is grown on a mechanical seal ring. We utilize sintered silicon carbide rings for most majority applications. There's some other hard face materials that could potentially be used, but majority it's going to be sintered silicon carbide. The diamond is grown directly on the surface of that ring using something called a Cvd process, which is a chemical vapor deposition process for the application. So utilizing gases within a vacuum chamber and some very high temperatures around 800 degrees C to form this diamond growth on the surface of that seal face. With this process is a very uniform growth rate on the surface of the seal ring, so overall there's no real impact in terms of the mechanical properties of the seal ring itself. What's novel about this particular diamond face treatment is the adhesion strength is astronomical. When typically you hear coatings or things of that nature, you tend to be concerned about delamination and flaking off of a coating. Well, because of the application and the process of applying this treatment to the seal face, and John Crane's done some testing in terms of adhesion strength per ASTM standards, the actual treatment adhesion strength is far greater than that of the silicon carbide substrate. So you will actually scratch the substrate surface before you actually remove any of the diamond face treatment from the surface of the seal ring. So very strong and robust material and adhesion to a substrate. So there's several advantages of using a diamond treatment in a mechanical seal application. Really what we're focusing on is low heat, low coefficient of friction, and what we can glean from those benefits. So what we will get out of that result is reduced energy cost due to the low coefficient of friction, so less heat generated. That's also less flush that you may require, so there's energy savings and cost savings there to be realized in terms of reprocessing fluids back into the mechanical seal. We also get ourselves some survivability in terms of intermittent dry running, upsets, things of that nature with startups, and typically when we lose lubrication in a mechanical seal, that'll be a killer for the seal. By utilizing the diamond treatment, we can give ourselves some insulation against those upsets and increase chances for survivability. So the robustness of diamond face treatment reduces a lot of the impacts of the operation. When we look at kind of a cross-section of typical mechanical seal face failures, the lubrication-related damage is inherently involved in one form or another in the greater percentage of seal failures. So again, the diamond treatment helps the seal faces survive these intermittent dry running events. On the screen here we have an example of application of diamond on diamond seal faces in a slurry seal in an aluminum plant. This is a caustic mud slurry, very difficult application with the process conditions that you see there. John Crane supplied several high-duty slurry seals with diamond seal face treatment to this application. They ran for 3 months, which was an acceptable feat in and of itself. Compared to the previous example, you can see all the leakage from the previous sealing philosophy in that picture in the center. After the 3 months, the pump was shut down for repair. The pump was restarted again, and they ran an additional 6 months. We're total 9 months on this application, which exceeded expectations by 3 times based on what the end user was looking for. So since that time, there's been another 8 pumps installed with diamond face treatment to similar slurry seals. And you can see after 9 months, this is the same pump in the bottom right here. A much different story in terms of the leakage and the condition of the base plate around the pump. So to kind of summarize a little bit, we've talked about application challenges, and really kind of the underlying theme here is we want to manage heat input to the seal face, optimize the interface lubrication, and control these variables so we have expected results that are in line with what end users are looking for in terms of leakage expectations. What we want to emphasize is there's no one size fits all. There's no one magic bullet to cover every single application. The devil is in the detail, so to speak. There's many available solutions, and John Crane engineering support and experience can really be tapped into to help solve example problem applications and really work on that principle of sealing the application and not just, putting a seal in a pump. Picking the right fix technology for the application and getting the most reliable and cost-effective solution is the ultimate goal. So with that, I will hand it back over to Mr. Parker, and we'll take some questions.
Well, thanks so much, Brian. Appreciate it. But we do have questions, and attendees, please send us your questions now if you haven't done so already. Jack, the first question is for you, and that is simply, is a seal support system always needed?
Well, in reality, is this what we mean by a seal support system? Every mechanical seal, apart from a mechanical seal that's fitted in a pump with API Plan 02, which is dead-ended, can be considered a seal support system. A pipe coming from discharge into the seal itself is a seal support system. So in reality, it depends on the application and what system you require for seal flushing, whether a single seal or a dual seal. Again, the only non-system that exists out there is Plan 02.
Good. Thank you so much. Brian, a question for you. In a dynamic lift upstream pumping seal, what happens when the shaft is not rotating? Won't the seal leak excessively?
Yeah, so in a dynamic lift USP seal, the seal faces are always loaded compressively by the process pressure. So they're always in compression due to the process pressure at the OD. The unique nature of the design allows for that pressurization of a lower pressure fluid between the seal faces, so we get that pressure spike that creates the separation in the dynamic lift. That all is a function of channeling that lower pressure fluid into those grooves and creating that hydrodynamic lift when the shaft is rotating. When the shaft is idle, the ungrooved portions of the faces contact at the OD and they create something called a sealing dam, and that prevents process leakage during static conditions. So because the hydrostatic pressure acting on the faces is significant to begin with due to the process pressure, that in conjunction with the sealing dam ensures that we don't have any process leakage when the shaft's in a static condition.
Thanks, Brian. Brian, another question for you. Listener asks, I have been told that diamond-treated seal faces can run dry indefinitely. Is this true?
That's not really an entirely true statement. So, while diamond and, the diamond treatment is a very hard, robust substance, diamond's probably the hardest material on the planet, material wear of a seal face is a complex metric that takes into account several things just besides the hardness of the material itself. There's abrasion, there's deformation of the seal rings due to the process fluctuations, there's chemical influences, and so on. So what happens in a dry running scenario is we've lost fluid film support. So in essence, that's a problem for a mechanical seal no matter what. With diamond treatment, the degree of wear is still greatly reduced, but it still occurs. And when we lose fluid film, we are still going to generate some heat and have some very minute wear. So localized temperatures will increase in this scenario, and while the seal faces are likely to survive, secondary elements such as your O-rings can be damaged, and so there's other underlying factors that you have to consider when you're thinking about running dry indefinitely. And you also want to consider that in real life, dry running scenario, the seal faces not only lose lubrication, but they're still under a load, and they're going to be impacted. So what I would say is a more accurate statement is that diamond treatment withstands intermittent dry running periods, and the duration of those periods, they can actually and have actually been demonstrated through very accurate testing. I know John Crane, we've done several in-house tests on intermittent dry running of diamond treated seal faces under load conditions, and have been able to establish some rather sound criteria on that topic. So,
thanks, Brian. Jack, a question for you. What is the recommended API plan for the laser face technology and spiral groove seal technology in hydrocarbon service?
Good question. In the laser face, as we mentioned earlier, the laser face is only to be running a liquid phase. The best API plan, or the recommended API plan for laser face, is API plan 11, which is a bypass from discharge, or API plan 13, which is reverse from stuffing box or from seal chamber back into suction when the differential or in the vertical services. The spiral groove technology is a completely different animal. This seal is a non-contacting seal, so it does run no contact, which runs on a cushion of vapor or vaporizing liquid. Once the liquid reaches it to the bottom of the spiral groove, it's normally running on vapor, and the leakage is vapor. The spiral groove seal or primary seal normally is running with plan 02, dead-ended. However, it is used as a dual seal, so the outer seal normally runs with plan 72 because of the vapor actually directed to a flare system. And sometimes we put a combination of plan 72, 62, which you inject a low pressure nitrogen to dilute whatever is leaked or the leakage from the primary seal and direct it into the flare system. So we look at the recommended plan is 02, 72, 76.
Good. We have about 2 minutes, a little less than 2 minutes remaining, so I'm going to try to ask 2 more questions. Brian, what is the best fluid to use between the faces in a dynamic lift upstream pumping seal?
Yeah, so the answer to that question is largely driven by what will the owner of that equipment accept going back into their process, because there is some migration of that fluid. From the seal perspective, a clean fluid is any clean fluid is best. So we've used anything from water to a light oil to even kerosene or distillate with USP type seals. So it really depends on availability and tolerance in terms of process migration.
Thanks, Brian. Jack, final question for you today. What is the laser face seal pressure limit?
Good question again. The laser face seal limit, it all depends on the actual seal that the laser face technology is added to. Normal seals, the API 682, 41 bar, the seal is actually handling that. However, we do have seals like the 8600 seal. It's running at 200 bar plus. So the pressure limit is actually dependent on the actual seal that the technology is added to the face.
Well, thanks, Jack. Unfortunately, that's all the time we have for questions today. I'd like to thank Brian and Jack, our expert speakers, as well as all those in attendance. We hope the webinar suited your purposes. In conclusion, I'd like to thank John Crane for sponsoring today's webcast. And now that we're just about done, we want to hear how we did. The exit survey will pop up on your screen as soon as this webcast ends. Please take a moment to complete it as we use this information to improve our webinars. On behalf of CFE Media and Technology, thanks for attending, and we'll see you next time.